final speaker is Zimeng Liu. He's a PhD student at Shanghai Jiaotang and is advisor to Shijing Zhao. And he'll be giving the final presentation before lunch.
Okay, hello everyone. I'm Zimeng Liu from Shanghai Jiaotang University. Today, I'm honored to share with you our paper titled FIGRET, Fine-Grained Robustness Enhanced Traffic Engineering. This is a joint work of Shanghai Jiaotang University and Tsinghua University. The authors also include Shijing Zhao, Yong Cui, and Xinbing Wang. Okay, let's begin by asking, why do we need robust traffic engineering? Both wide area network and data center network began to use traffic engineering to optimize network performance. For example, Google and Microsoft have implemented traffic engineering in their WAN, P4, and SWAN, respectively. As for the data center network, the traditional closed data center use ECMP to routing, and there's no need for traffic engineering. But due to the fact that the electrical switching become cost and energy prohibitive to keep up with the bandwidth scaling, so some data centers, such as Google's Jupyter, began to use optical switching as their core layer. And the optical switching offers a topological reconfigurability, so the network operators also employs topological and traffic engineering to optimize network performance. One challenge for traffic engineering is the occurrence of traffic bursts, especially in the data center networks. And there are many microsecond small flow, and so the bursts are prevalent. However, due to the fact that the convergence time for traffic engineering can reach to second level, so it is too late to wait until the burst is detected to then perform traffic engineering. So the traffic engineering need to be based on the historical traffic demands to develop T solutions that are robust enough to the traffic burst. And then, before delving into the details, I'd like to give some more background to you about the traffic engineering. Given a network topology and a traffic demand, the TE controller will solve a multi-commodity optimization problem to develop the TE solution and to determine the best distribution of the flow. But one issue is that the TE solution from the multi-commodity flow optimization often have many paths with split ratio close to 1, which indicated that the traffic is too dependent on a single path and to manage the burst. And when the burst occur, it will lead to significant congestion. To show this, we test on one data center pod level and tower level, and the max link utilization over time is demonstrated in there. And from the result, you can see there are many peaks in the result, and the peaks are is caused by the traffic burst. To handle the traffic burst, existing TE method have adopted robust optimization to handle the traffic burst. And first is a demand prediction-based TE. It first predicts the demand and then optimize the multi-commodity flow optimization based on the predicted demand. It does not take any action to the traffic burst, so it will have low performance when the burst will occur. And the second method is the demand oblivious TE, which optimizes for the worst case performance for all possible demand to guarantee the robustness. However, since it does not use the historical traffic information and its performance in non-burst scenarios will be scarified. And the COPE is optimized based on the predicted traffic demand and then provide a bounded for the worst case performance. It uses the historical data. but it has a problem that its scalability is very poor because it optimizes for all the possible demand. Okay, so the first method is a hedging mechanism, which is used in Google's Jupyter Data Center network. As we said in the previous slides, and the poor performance of the T solution is because they rely on one single path. So hedging mechanism set an upper bound on the split ratio and force the traffic to spread across multiple paths to avoid congestion. However, it still scarifies the performance in non-burst situation because it forces all the SD pair to spread across multiple paths rather than the best path. And we also show the result we test on the 3 data we mentioned earlier. And from the result, you can see compared to the multi-commodity flow optimization, and the peak of the MLU indeed decreased, but the choice is increased, and which indicated that it is a suboptimal performance for the non-burst situations. So from this result, you can see there is a trade-off for traffic engineering in burst and non-burst situations, and the existing method cannot handle this trade-off. So FIGRET is designed to solve these issues, and we found that the existing method scarifies the non-burst case performance because they treat all source destination pair equally, which is inappropriate because the traffic characteristic of the source destination pair is vary. So we designed a fine-grained robustness enhancement method that tailors the strategy based on the burstness of each SD pair, achieving balanced performance. What's more, we found if we use linear programming to implement FIGRET, and the complexity is very high, so we implement this algorithm using deep learning. And then let's reconsider the hedging mechanism to get the insight to improve it. Hedging mechanism forces all SD pair to spread across multiple paths. But is it appropriate to treat all SD pair equally? To answer this question, we display the burstness of the 3 data we mentioned earlier, and the color of the square care in the small square in the picture represents the burstness of the source destination pair. And from the result, we can see the characteristic of the source destination pair is vary. Some SD pair is indeed burst, but there are many other SD pairs is quite stable. Enhancing robust for this stable SD pair is unnecessary, and so our insight is to tailor the strategy for each SD pair according to their characteristic. And we use an example to show the advantages of this insight. Let's consider a simple scenario that has 3 nodes interconnected. And in normal, the traffic from A to B, A to C, and B to C is 1. And the burst only occur between B and C, and surging to 4. And there are 3 strategies. And the first strategy allows all pairs to use the best path. And the strategy 2 forces all pairs to use the multiple paths. And on the other hand, the strategy 3 only enhances the robustness between the BC pair, and only forcing the BC pair to use the multiple paths. And then you can see the result. The strategy 3 is better than strategy 2 in both non-burst and burst situations. So we can see the advantages from this example. So FIGRET is designed based on this insight. And before we implement this insight, we need to determine how to quantify the robustness. And consider a path with a split ratio of RP. And if the SD pairs traffic burst by delta ST, then the burst traffic split on 2 paths B can be calculated as the RP multi-delta st. And then the increase of the edge on this path can be calculated as RP multiplied delta st divided by the capacity of the edge. So if we take the capacity of the bottleneck edge as the capacity of the path, and the max impact of the path can be calculated by this. And from this equation, you can see the impact of the burst traffic is related to the red factor, and we call the path sensitive. The smaller the path sensitive is, the less impact the traffic on the path. And so we use the path sensitive to quantify the robustness. Okay, we have determined how to quantify the robustness, and then we can formulate the FIGRET as follows. As you see, compared to the multi-commodity flow optimization, it is a new constraint that asks the path sensitive remains on customer's threshold. And then the next question is how to solve the TE model. It should note that so far we have not determined how to solve for the predict traffic demand and the path sensitive constraint, right? So the first method is a two-stage method, and we first estimate the predict demand and the path sensitive constraint, and then employ a linear programming based to solve the TE model. But it have two drawbacks, and the first is there is a mismatch between the prediction task and the optimization task. And here is an example in the red figure. And from that figure, you can see the same prediction accuracy leads to different max link utilization. That is because for optimization, it is more critical to predict accurately the demand on the path with a small capacity. But the prediction tasks do not account for the network topology. And the second drawback is that the two-stage method have high runtimes and low scalability, because compared to the multi-commodity flow optimization, it is a new constraints, and the new constraints will make the TE model hard to solve. So a better approach is to use a deep neural network to establish a mapping between the TE solution, between the historical demand and the TE solution. It eliminates the mismatch between the prediction and the max link solution optimization, and it is it is faster and more scalable. But there are the challenges. How should we transform the new constraint into the loss function design? First, let's take a look at the Lagrangian relaxation of the TE model. And from this equation, you can see there are two components, and which indicated that the loss function of FIGRET should have two components. And the first component is to minimize the max link utilization. And the second component is related to the fine-grained robustness enhanced. But we didn't explicitly solve for the path-sensitive constraint, right? So we cannot directly calculate the loss for the fine-grained robustness enhanced by the second term of the Lagrangian relaxation. Next slide, please. Okay. And so we design a historical scheme to capture the insight. And for each ST pair, the loss for each ST pair can be calculated by the variance of the traffic demands, multiply the max path sensitive among the pairs serving for this ST pair. And the loss for the second, and the loss for the fine-grained robustness enhancement is the sum of all loss of source destination pair. So how this loss captures the insight of fine-grained robustness enhanced, and if the pair is prone to burst, it will have a high variance of its traffic, and it leads to the high value of the loss. So during training, we want to minimize the loss, and we will lower the path sensitive and the low pace-sensitive indicates high robustness. And so you can see as follows: the loss for FIGRET can be calculated like this, and there are two components. And the first is max link utilization loss, and the second is pace-sensitive loss. Okay, so the last question is how to design the structure for FIGRET. And existing TE method have, for example, TIL use a graph neural network to handle network topology, and DOT use just fully connected network. So I want to discuss here whether we need to use a graph neural network to handle the network topology. We need the topology in TE because given a traffic demand and a TE solution, we need to calculate the max link utilization based on the topology. So let's take an exam between the relationship. Let's take an exam between the relationship between the TE solution, objective, and topology. So given a traffic demand, we need to know which set of pace serves for this SD pair, and to determine the total demand for each pace set. And then, according to the TE solution, we can calculate the demand on each pace. And last, if we, by knowing the age each pace passes through, we can calculate the total demand on each pace and then the age utilization. So from this process, you can see the topology information required by traffic engineering is explicit and known, is SD to pace and pace to age. So if we're using SD to pace and pace to age, we can establish a direct equation relating the TE solution, objective, and topology. So there is no need to use graph neural network to learn the topology information, and use a fully connected network is enough. So by now we have introduced the fine-grained the FIGRET's loss function as a structure, and then let's look at its performance. Previous slides, please. Previous slides. Okay, and first is experimental setup. And the network we test on network topology includes one and the data center network with no number ranging from tens to hundreds, and the traffic characteristic also exhibit varies, including profiles with low, moderate, and high burstness, and there's a base length. Next slide, please. And the first is TE quality. And from the result, you can see the FIGRET can better balance the performance between the burst and non-burst scenarios. And compared to the hedging mechanism using in Google's Jupyter Data Center, FIGRET achieve a reduction in max link utilization. And compared to DOT, an algorithm not consider burst, and FIGRET reduce significant congestion events. As for the solver time, since FIGRET is implemented by deep neural network, the inference time of a neural network is shorter than the calculation time for an optimization problem. So the calculation time is short. And as for the training time, since FIGRET is designed based fully connected network and directly loss minimization, and its train time is less than the TE method use graph neural network and reinforcement learning. Okay, we also provide an interpretability for FIGRET's effectiveness. We compare hedging mechanism and FIGRET, and we analyze the relationship between the TE solution and the traffic characteristic. And from the result, you can see FIGRET can enhance fine-grained robustness based on the traffic characteristic. And there are more results in papers. So in conclusion, we propose FIGRET, a fine-grained robust enhanced traffic engineering, which can achieve better balance in non-burst and burst scenarios. And FIGRET has faster calculation time and faster training time. FIGRET also provides an interpretation of its effectiveness. That's all. Thank you.
I wanted to know what burst lengths you can tolerate using this approach. What can the burst lengths be? Like, what's the smallest burst you can tolerate using this in terms of time?
I'm sorry,
The
I don't
duration of the
understand.
burst that you can tolerate using this approach. The duration of the bursts using this approach, do you have any sense of what durations you can tolerate with this approach? When you have traffic bursts, how big can they be?
So you mean how to determine which
Yeah.
traffic is burst, right?
Yeah.
And we can just calculate the variance of the traffic demand in the historical data to determine the burst traffic.
All right, I think that concludes the session. We have lunch next in the program. Thanks all for attending.